Okay, so we're going to do probability today. This is our biggest probability note today. So I'm just going to throw everything at you because we're going to take it from here and we're going to start doing kind of problems. Because the biggest thing with probability, there's not a ton of rules. It really is just kind of reading the problem and figuring it out. So today I'm going to kind of throw everything at you. So probability of an event E, we write it as probability, so parentheses E. It's the number of favorable outcomes over the total amount of outcomes. So this value measures the likelihood that an outcome will occur. It always falls between 0 and 1. So you can never have a negative probability, and you can't have a probability more than 1. So for example, rolling a die or selecting a card from a deck are chance experiments that have equally likely outcomes. The probability of rolling a 6 is 1 out of 6. So there's one outcome, here's your 6 total. Rolling an even number is 3 6. So you must reduce your fractions. Okay, I don't care if you write your answer as a fraction, a decimal, or a percent. Usually what I tell students is it kind of depends on the problem. Obviously with what we're doing here, fractions a lot easier. There'll be some where a decimal will be a lot easier when we get into Venn diagrams. If you want to convert to a percentage, you can, but it doesn't matter. Usually on my answer key, I have all of them. Okay, drawing the queen of spades, that's 1 out of 52. And then drawing any queen, again, would be 4 out of 52, so 1/13. The only thing we will take off points on is if you do not reduce your fractions. So the law of large numbers says that as the number of trials of an experiment increase, the relative frequency of that event will approach the true probability of that event. So basically what happens, the more you flip a coin, the closer you get to 50-50. Some basic properties of probability. Again, for any event, the probability has to be between 0 and 1. If the probability is 1, that means the event is certain to happen, 100% chance. If the probability of the event is 0, that means it's impossible, won't happen. But usually, very rarely do we have a 0 or a 1. If S is the sample space for the experiment, the probability of S is actually already equal to 1. If two events are disjoint or mutually exclusive, then the probability of E or F happening is just the probability of E plus the probability of F. Think about, we talked about mutually exclusive yesterday. They don't have anything in common. So I could just add them together. So the probability when I'm rolling one die that I get a 1 or a 2 would be 1/6 plus 1/6. So 1/3. The probability I get a 2 or an odd, again, probability of 2 or an odd, that would be 1/6. Odd would be 3/6. So 4/6 or 2/3. This works for more than 2 disjoint events as well. You could just keep adding. If they're not disjoint, what ends up happening is you use this formula. The probability of A or B is A plus B minus the overlap. This is the only 2 rules you're going to need in all of Chapter 6. We'll get to this later. But this one works for everything. If they're mutually exclusive, A and B are just 0. The complement rule, the probability of E and not E should add up to 1. So if the probability that it rains is 30%, the probability that it doesn't rain should be 70%. So probability distribution is the next thing. We're going to really look at probability distributions a lot in Chapter 7, but you'll see them throughout chapter 6 because sometimes I'll give examples from there. So probability distribution is a list of all the outcomes in the sample space and their probability. So what should happen is there should be no negatives, and they have to add to 1. Okay, the table should add to 1. So here, the probability I get an E, well, if I add all three of these together, I get 0.95. So the probability I get an E is 0.05, because they should all equal 1. So this is 0.05. C or better, I'm just going to add C, D, and E. Oh, sorry, C, B, A, 0.4, 0.3, 0.1, so 0.8. Not an A, you can do 1 minus 0.1, or you could add B, C, D, and E together. Either way, you get 0.9. So what is the probability distribution for the sum of two dice? We're going to use the sum of two dice a lot throughout the chapter, so you can always Google it. But basically, here's what the table looks like. So we have two dice, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And we're going to add them all together. So I get a 2. So I'm just adding the row and the column. And you can always Google this for homework. Usually if it shows up on a quiz or a test, I'll put it on the board. Okay, so if I want the probability distribution of the sum of two dice, the sum can either be from 2 to 12. So on the one side, I'm going to have sum, and I'm going to write kind of small, and then you have your probability. So I can have 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So to get a sum of 2, that only happens once. So that's 1 out of 36. To get a sum of 3, that's twice. So 2 out of 36 reduces to 1/18. 4 would be 3 out of 36, or 1/12. 5 would be 4 out of 36, 1/9. 6 is 5 out of 36. 7 is 6 out of 36, so 1/6. Now the nice thing about this table is it actually is symmetrical. So this is 5 out of 36, 1/9, 1/12, 1/18, and 1/36. Okay, so the probability that the sum I get is even. So if I were to add 2, 4, 6, 8, 10, 12, or if I just thought about it, your sum's either even or odd. So either way, the probability should be a half. A sum greater than 4, or sorry, less than or equal to 4. So I can have a 2, a 3, or a 4. Now you don't necessarily have to write all this down every time. I'm just doing this because it's notes. It is helpful kind of in your head. So 2 was 1/36, 3 was 1/18, and 4 was 1/12. And you should get 1/6. Now, it seems like a lot, but you're going to have to show all your work. This is showing work, so it doesn't seem like it's a lot of work to show, but I need to see this because I need to be able to see what you're thinking. The sum is less than 12. Well, I could add up 2 through 11. Or here's where using the complement could be easy. I would just do 1 minus the probability I get a 12. So 1 minus 1/36 would be 35/36. So we use coin problems a lot. Suppose you flip a coin 3 times. What are the 8 possible outcomes? So again, we could have heads, 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 tails, heads, tails, heads, tails, heads, heads, 2 tails and a head in any one way, or all tails. Are these all equally likely to happen? At this point, yes. So the probability that I get 2 heads when I flip a coin 3 times, there's 3 ways that can happen. So that would be 3/8. So on the next page, if I make a probability distribution, you have the number of heads, and then again you have the probability. I could have 0 heads, 1, 2, or 3. Well, we already figured out 3 was 3/8. Getting 1 head is also 3/8. Getting no heads would be tails, 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 that's 1/8. And getting 3 heads, it's heads, 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 so that's 1/8. So the probability you get at least one, let's switch this to at least 1 head. Again, at least 1 head. You could add up 1, 2, 3, or you can do 1 minus the probability you get no head. So either way you get 7/8. So sometimes there's multiple ways to do this. It just depends on how you think about it. Again, that's why I need to see this work, especially with the P in the parentheses that's telling me you're doing probability. So again, there's more examples. Again, I'm throwing you everything I could think of. Here's a Venn diagram. So we have A, B, and then we have some stuff outside A. Again, all of this is decimal, so I'm going to leave my answers all in decimals. So the probability of event A is just 0.16 plus 0.31. Zoom in a little. So that would be 0.47. Probability of B, I'm going to add up 0.31 and 0.5. So 0.81. A or B, anything in A, anything in B, or both. So 0.16 plus 0.31 plus 0.5. So 0.97. A and B would just be the intersection. So 0.31. Anything not in A, so you can do this 2 ways. You can look at the Venn diagram and think what's not in A and add up those 2. Or you can do 1 minus what you did in part A. Either way you get 0.53. Not A and not B. So anything not in A and not in B would be everything on the outside. So that's that 3%. The intersection, whatever's not in the intersection. So if you think the intersection is just this 0.31, you're looking at everything not in the intersection. So 1 minus 0.31. So 0.69. So you've seen Venn diagrams. We've done some probability distributions. You will also see things in a table form. So example 2 down here is a table. A study of women who had a breast lump investigated whether or not each woman received a mammogram and a biopsy. So the event A is that they're 65 or older. The event B is that they had tests done. So what's the probability that they're 65 or older? 0.365 plus 0.19. So just 0.555. The probability that they had tests done, I'm going to add this whole row and column. 0.321 plus 0.365, so 0.686. Now unfortunately the other stuff's on the back, but I'm going to rewrite the table so that you can see it. So the probability of A or B, so either 65 plus or they had tests done, So I'm going to add up 0.321, 0.365, and 0.19. So 0.876. The probability of A and B, so A and B would be that they're 65 or older and they had tests done. So 65 and older, test done, 0.365. So E here defined the probability of not A and not B. So again, that would be under 65 and no test. So you just look at under 65, no test, and you end up with 0.124. F, again, the complement of the intersection, I'm just going to do 1 minus the intersection. So 0.635. Okay, so we had a table, we've had a Venn diagram. The next two are just story problems. Again, we're just kind of throwing everything at you. So an individual has presented with 3 different types of glasses of cola, labeled C, D, and P. He's asked to taste all 3, then list them in order of preference. Suppose that the same cola has actually been put into all 3 glasses. What are the simple events of this chance experiment, and what probability would you assign to each one? So let's list everything. So he can start off with CDP or CPD. He can do P first, or he can do D first. So those are my 6 outcomes. Each one of them is a probability of 1/6 because they're the same. What's the probability that C is ranked first? So C is first. Well, again, that's 2 out of my 6 outcomes, so 1/3. What's the probability C is ranked first and D is ranked last? C first, D last. That's only 1 out of 6. Okay, a student placement center has a request from 5 students for interviews regarding employment with a particular consulting firm. 3 of these students, 1, 2, and 3, are math majors, and the other 2 are statistics majors. Unfortunately, the interviewer has time to talk to only 2 of the students. These 2 will be randomly selected from among the 5. So, a few things you got to keep in mind when you're doing this problem. First of all, 1-1 does not happen. So you can't have the same person interview twice. So that's one thing to keep into account. And order doesn't matter. Okay. So I'm going to list the outcomes. So I could go 1, 2, 1, 3, 1, 4. Now when I start with my 2s, again, 2, 1, and 1, 2 are going to be the same thing. So I could have, 1, 5. I missed the 5th person. So I could have 2, 3, 2, 4, 2, 5, 3, 4, 3, 5, or just 4, 5. Okay, so there's 10 outcomes. What's the probability both are selected are stats majors? Well, that would be if I interviewed person 4 and person 5, so 1/10. One way for that to happen. What's the probability that both students are selected are math majors? So you want a combo of 1, 2, or 3. So that would be 1, 2, 1, 3, and 2, 3. So 3/10. What's the probability at least one of these students selected is a stats major? Now, here's the thing about at least one. You can go through and figure out all the 4s and all the 5s. Or sometimes it's easier to just do 1 minus that they're both math. Because that would be the complement. which we already figured out. So 1 out of 3 minus 3/10, so 7/10. Or you could just count which one has a 1, it has a 4 or a 5 in it. Either way, you should get 7/10. What's the probability that they have different majors? Again, instead of going through and looking at different majors, what I'm going to do 1 minus the probability that they're both math minus the probability that they're both stat majors. Because then I don't have to count like, okay, different majors, one, it's a lot to think about. But I already know that there was one way for them to be, or 3 ways for them to be both math, 1 way for them to be both stats. So that's 6/10 left over, or 3/5. Okay, so a lot of this stuff, again, it's going to be you kind of trying it on your own. We're going to spend a couple days kind of just doing problems, which I think will be a lot more helpful than just sitting here doing notes, because this was a lot in 20 minutes.